To analyze the problem of normal modes in a general way, we start from an arbitrary Lagrangian, which is always defined as T minus V, where T is the kinetic energy and V is the potential energy. And we used generalized coordinates. Those are the Qj, where the j run from 1 to some number k. And we can express the positions of the particles in terms of these generalized coordinates. Assuming that there is no explicit time dependence, we can write Ri therefore as a function of the Qj, where I, the particles, they run from 1 to n, because there are n particles in the system. We can then also write the velocities of the particles in terms of these Qj, because the Qj carry the time dependence. And this results in r dot I, which is the velocity as a function of Qj. And then we use the chain rule. It's equal to dri dqj. And then we multiply by Qj dot. Evaluating then the kinetic energy, which can be written as a half times the sum over all the particles. The sum over I always runs from 1 to n, times mi r dot I squared, gives me 1/2 times the sum over mi, and then I have replaced the first ri dot here by an expression like this, and then a similar expression for the second one, because there are two ri dots here multiplied by each other, and I've taken care not to use the same summation variable, so I use here a j and there I use a k, but apart from that these are identical. And then I can streamline this expression by just reordering the sums. So in this case I've put the sum over j and over k in front of the expression, and now in the parentheses there is the sum over mi, or sum over I with an mi, and then these two terms. And because I sum over I, this term does no longer depend on I itself, it only depends on j and k, and I call it mjk. And if I do that, I see that I get a very simple form for the kinetic energy. It's just a half times the sum over j and k, mjk, q dot j, q dot k. So the m is a kind of generalized mass. It's a matrix because it has two indices associated with the generalized coordinates qj and qk. Let us now specify the problem we are looking at. That problem is small deviations of a system from equilibrium. And equilibrium is reached when there is no force acting on the particles, and we assume that we have a system without any explicit external time dependence, no time dependence in the constraints. And in that case, the generalized coordinates, they can remain the same, they can stand still, provided the potential has reached its minimum, and that is achieved when dV dqj is 0. So that is an equilibrium condition, and that holds for systems which have no external time dependence. It's anyhow very difficult to reach an equilibrium stage when a system is subject to external influences that are time dependent. So we assume that they are not there, and that we have a usual system, in quotation marks, for which the equilibrium is achieved when dV dqj is 0 for each qj. Now previously we have seen that the t can be written in this particular form, so let us see what the v does in this case. The v can be written as a function of all the generalized coordinates q1 up to qk, and we can write it as an expansion around the equilibrium point, and the equilibrium point is indicated with a tilde. So q1 up to qj tilde, qk. And then we have correction terms. We can get a handle on these correction terms by doing a Taylor expansion around the qj tildes, and the first order Taylor expansion gives me this correction, so it's deviation of qj from the q tilde, and then we have the first derivative of v, but we had agreed that the v dqj would be 0 at equilibrium. Q tilde is the equilibrium state, so in this case the first order Taylor expansion vanishes. So we include the second order Taylor expansion, and we find that from the second derivative of v with respect to qj and qk, and then we multiply by the deviation of qj from qj tilde and the deviation of qk from qk tilde, and the v, here is the derivative of the v, is to be taken at the equilibrium point, which is the set of all the qj tildes. In order to elucidate the structure of the result, we define v at equilibrium point simply by v tilde, as v tilde. Then we take the derivative of qj from its equilibrium as delta qj, and therefore qk minus qk tilde is delta qk. And the second derivative of the potential with respect to qj and qk is abbreviated by the symbol kjk. And then we obtain the following form. We have that v for k1 to qk1 to qk is the v at equilibrium point plus a bilinear form in the deviations of v from the equilibrium point, and in principle we could add of course higher order terms, but we will restrict ourselves to second order expansions in terms of the deviation from the equilibrium. In order to highlight the similarity of the expansion for v and t, we have repeated here the expression for t, and then we have written it also in terms of the delta qj dot rather than the qj dot themselves, and we can do that because the delta qj is defined as qj minus qj tilde. Now the qj tilde is the position of the generalized coordinate j at equilibrium, so that is a fixed value, it's time independent, and therefore when we take the derivative with respect to time, this disappears and I can identify the qj dot by the delta qj dot. And we see that together with this equation we have two very similar expansions, so up to this vector of v tilde, which is of course irrelevant because it's just an offset of the total energy. We could always choose the total energy such that this term vanishes. And so up to that first term the expansions are very similar. The difference is that in this case we have an expansion in the delta qj dot, and here we have an expansion in the delta qj, and the matrices obviously are different. This is the second derivative of the potential with respect to qj and qk, and the mjk is the second derivative of the kinetic energy with respect to qj dot and qk dot. So in order to simplify the notation, I will not keep using the delta q, but I will just write it as q. So from now on, when you read a qj, it is in fact delta qj in this language here. And I can write this q, which is a vector, as a column vector, q1, qk. I could also consider the qt, that's the transpose of the column vector, and that will become a row vector, q1 running up to qk. And if I have those two definitions, I can write, for example here, the kinetic energy in the following form. I can write it in the form a half qt, and then I write here the matrix M, and then I write q. Half times q dot t, that's the row vector, multiplied by the matrix and then multiplied by the column vector q dot. And if I write all the elements out, I see something like this: half times the row vector. Here you see the components, and then this is the matrix elements of the matrix M, and here the column vector. If I multiply a matrix by a column vector, the result is a column vector, so this is a column vector, and if I take the product with the row vector, I get a number, and that number represents then the kinetic energy. And in shorthand notation I can do the same for the V, which is the V at equilibrium plus the deviation to second order, and the deviation to second order can also be written as a row vector, product with a matrix, and then product with a column vector. And so this then gives me the Lagrangian in the following form. So again, the V tilde is an irrelevant constant, and so the two important terms can be written as products between row vector, matrix, and column vector. And so this is the starting point for working out the equations of motion. But before we do that, we realize first of all that these matrices are both symmetric. To see this, we consider again the definition of MJK, which is the sum of I, MI, DRI, DQJ, DRI, DQK. And you can see that when I swap these two terms, adjust the product, you have the same result, and therefore the MJK is equal to MKJ. In other words, M is a symmetric matrix. And we can do a similar analysis for the KJK, which is the second derivative of the potential with respect to QJ and QK. And if we swap these two derivatives, then if the function V is not too wild a function of the generalized coordinates, that gives us the same result, and we find that also the matrix K is symmetric. So the conclusion is that the matrices M and KJ are symmetric. The fact that M and K are symmetric is very important when we want to formulate the equations of motion, because, for example, let's have a look at dl dq dot j. So we need to take the derivative of this term, and that can be written obviously as 1/2 d dq dot j, and then we write out this vector matrix, vector product, in terms of the coordinates, in terms of the elements. And then we see that this j has a fixed value, but we sum over the l and the k. So this l may become equal to j, and then it drops out because of taking the derivative. And then we have an expression like this, but with a factor 1/2. But the same can happen when we take the derivative with respect to q dot k. K will also assume the value j, and then we have a term q dot l times mlj, and because m is symmetric in the indices, we can also write that in this form. So the factor of 1/2 is compensated by the factor. We have two contributions, and to be more specific, I work out an example here where we have only 2 degrees of freedom. So then I can write out this expression. It's q1 dot m11 q1 dot, and then we have here a q1 dot q2 dot q2 dot q1 dot q2 dot q2 dot with the appropriate matrix elements. And because these matrix elements are the same due to the symmetry of M, we can immediately find that when we take, for example, the derivative of t with respect to the q1 dot, that we have m11 q1 dot plus m12 q dot 2. And that's precisely this form. And by the way, obviously the derivative of L with respect to q dot j only derives from the kinetic energy, because the potential energy does not depend on the q dot j. So writing dl dq dot j or dt dq dot j doesn't make a difference. We also need the derivative of the Lagrangian with respect to the qj, and that derives from the term with the minus kjk. That term has a form very similar to the one with the m, and so the analysis proceeds along exactly the same lines, and we arrive at a very similar result, which is that the LDQJ is minus the matrix K times the vector Q, and then the jth component. So then we can write up the Lagrange equations of motion. We have d dt dl q dot j. That has this form here, m times q dot, and we take the jth component, and that should be equal to the dl dqj, which, as we just have seen, is minus matrix K times vector Q, and then the jth component. So now it is a bit subtle how to tackle this term, because one contribution is, of course, when we take the derivative with respect to this Q in order to give us a Q dot dot. In fact, then we have a term which is linear in Q on the left hand side and linear in Q on the right hand side. Now there is obviously a second contribution coming from the derivative of m, because m depends on the generalized coordinates. But if we take the derivative with respect to time of m, we get contributions proportional to q dot, and together with this q dot, that gives terms here that are quadratic in the q's. And we want to keep only the lowest order terms, so the terms that arise from taking the derivative of m with respect to q are neglected in this analysis, and so this is the equation we end up with. And just as in the previous movie with two springs and a pendulum, we anticipate that there can be a solution in which all the QJs vibrate at exactly the same frequency. So I write the vector Q in the form A, which is an amplitude, which is time independent, times an e to the power I omega t. And all the degrees of freedom vibrate at the same frequency, and that is expressed in that the omega does not depend on J. So for each J, the omega is the same. And if we write up this form of the solution, this ansatz, then we can immediately see that the q dot dot gives me a minus omega squared times the q, and we can plug that back into this equation. We then arrive at this form, minus omega squared matrix m times vector A times e to the power I omega t is minus matrix K times vector A times e to the power I omega t, and I can just cross this one out because it occurs on the left and on the right hand side, and what we are left with is again a generalized eigenvalue problem. And so this problem can be solved on a computer. There are usually routines available in any computer language or mathematical environment which can solve the generalized eigenvalue problem. Usually, of course, we also take a plus on the left and right hand side. And the other way to solve this equation is by looking at the determinant of omega squared m minus k, and that determinant should vanish in order to allow for a non-trivial solution A of this equation, and that gives me a polynomial equation in omega squared. So for a 2 by 2 matrix is generally a quadratic form in terms of omega squared. We can solve that, and then we take omega is plus or minus the roots of that quadratic equation. So let us now revisit the example that I have covered in detail in a previous movie. The example that we have considered was a mass held in position by two identical springs. The mass can move only in the horizontal direction, and we associate a generalized coordinate x with that motion. Then there is a mass capital M, which is suspended to a pendulum, which is attached to the little m, and there is a generalized coordinate phi associated with the pendulum. And in the movie in the previous movie I have already derived a Hamiltonian, which then turns out to have this particular form. Now that is the general expression, and we are interested in this Lagrangian close to equilibrium, and in equilibrium obviously the x is 0, then the little m is exactly in the center, and the phi is also 0 because then the pendulum is suspended in a vertical position. For the x there is no need to do anything, but for the phi, which occurs in the cosine twice, we need to expand, and I expand to second order in phi, and so the cosine phi is then 1 minus phi squared over 2, and I should do that here, but a term with phi squared multiplied by the x dot and the phi dot is fourth order in the phi and the x, so we neglect that contribution in this term. However, in the last term there is also a cosine of phi, and there I expand it in the second order because there's nothing else in front of this, which is small. And so this is the Lagrangian expanded to second order in the coordinates, and that's what we anticipate because previously we had seen that always the Lagrangian is bilinear in the velocity, so bilinear in the qj dots, and it's also bilinear in the qj's, so in the x and the phi. So this is correct Lagrangian. And so now the question is to find the matrix M, and we had a definition of M which was the following. MJK is the sum over I, MI, DRI, DQJ, DRI, DQK. However, this is a rather complicated form, and we don't need to calculate M using this formula. It is much easier if we just inspect the form of L, and in particular its dependence on the qj dot, so in this case the x dot and the phi dot, and then try to read off the form of the matrix MJK directly from that. That is done as follows. Here I have the matrix M. It doesn't have the elements yet filled in. I have indicated in red that the first index corresponds to the x dot and the second one to the phi dot. And so I can now fill in these elements. So the x dot squared, that is determined, the coefficient of x dot squared is determined by the upper left element, and we see that it's little m plus m. Recall that the Lagrangian was given as a half times the q dot t vector, and then the matrix q dot. So the factor 1/2 is already here included, and I don't need that. I should not put that in there. Let's complete this expression: half qt k q, and then we fill in the rest of the terms. So the lower right is the one corresponding to the phi dot squared, as you can see, and therefore I have a ml squared there. And then we have these two elements which represent the coupling between x dot and phi dot, and as you can see here, that should add up to ml, but it is not prescribed, of course, how we should distribute that. Sure, there can be contribution from here and from there. They both couple to x dot phi dot, but we know that the matrix should be symmetric, and therefore we put an ml in here and an ml in there, and then these two terms add up to 2 ml x dot phi dot, and then together with this factor of half, it precisely fits the form that we have there. And we can immediately write up the K matrix in the same way, and we see that there is no coupling between x and phi. There are no terms x times phi, and from that it follows immediately that a K matrix has the following form. It has a kappa coupling to the x. So let's put the variables here. It's here x and phi, not the dots. And we have a 0 on the diagonals, and here there is a MGL. Looking at this matrix, it is clear that we can divide the second row by ML, because that's present here in all the elements. And then we have simplified versions, or somewhat cleaner versions of the matrices, and they read M has now a simpler second row and K as well. And if you have paid attention in the previous movie in which I analyzed this model without this formal expansion of the L in terms of matrices, you should recognize that there I had exactly the same form of M, and I had exactly the same form of K, and I will give them a prime in order to distinguish them from these versions. So you can always multiply the rows of both matrices by a particular constant. The analysis then of the previous movie tells you how you find the normal mode frequencies. We therefore need to solve the following generalized eigenvalue problem, and if I write out the matrices, if I use the form of M and K that we have just obtained, and in fact I use here the primed versions because they are somewhat simpler, I find that this determinant should be 0, and that gives me a second order equation in terms of the omega squared, which I can solve right away. And then using those values for omega, I can also identify the eigenvectors which form the amplitudes of the normal modes. So I think in conclusion it is important to note that we have used this expression in particular in order to show that L can always be written in this form which involves the matrices. Let's see where, yes, this is the form I'm looking for. And if you then evaluate the Lagrange equations and you use matrix notation, you find that they always have this form. You can find for these equations always a normal mode solution, which is this solution here. And if you plug that in, it turns out that you have to solve this generalized eigenvalue problem. But I guess the most important message is that the easiest way to find the mass matrix M and also the Hessian matrix K, it's called the Hessian matrix, is the second derivative of the potential, is to just look at the Lagrangian that you have formulated for the problem and that you have expanded to second order in the deviations from equilibrium. So those are the x and the phi. And then once you have identified that Lagrangian, you can directly read off the matrix M and the matrix K and then proceed with the solution.